segregate the duplicated genome into datasets. Now, a third form of transmitted microscopy that takes advantages of refractive indices properties of the specimen is polarization microscopy. But here, rather than like in phase contrast, looking at the difference between the refractive index and the background, giving, in this case, a dark contrast for this clump of ribosomes, right? And polarization microscopy is the difference in refractive index in different directions in the specimen. That is, the optical anisotropy represented by two different refractive indices, one for light that's vibrating with its electric vector this way, and one for light vibrating with its vector in a perpendicular direction. And for this isolated mitotic spindle, in phase contrast with polarized light, that by the fringes, that is, the two different refractive indices, arise from a form anisotropy due to the microtubules, the 25 nanometer diameter microtubules, that are all lined up roughly parallel to each other that make up the spindle fibers within the central spindle. They also make up the fibers of the astral rays, and these astral rays are lined in the same direction as those in the central spindle, and they have the same contrast in this polarized micrograph. Those are lined in a perpendicular direction with a dark contrast, and I'll explain where that comes from shortly. Let me begin by reminding you that the light propagates, in this case in the z-axis direction, as it transfers vibrating electrical and magnetic wave. The vibrations are perpendicular to the direction of the propagation. The velocity of propagation, V, is given by c divided by m. M is the refractive index, and c is the velocity that light would have in a vacuum. It's very similar in there. And n is the refractive index of the medium through which the light is propagating. Now, this plane polarized light has its electric field vector oscillating within a plane, and if you look, I can't do this here, right, but if you look down the z-axis, as shown here, if it's plane polarized light, then this oscillation stays with its vector in this plane, and it can be defined by a given azimuth angle, theta in this case, relative to, let's say, an xy coordinate system that's orthogonal to the z-axis of propagation. Lasers, for example, are polarized light from coherent sources within the laser. On the other hand, the tungsten filament has many molecular oscillators that emit light asynchronously in different orientations, and one gets, as a result, unpolarized light with electric vectors in many different directions. And this is typical for most of the light sources that we encounter, including arc lamps and tungsten filaments that are used in light microscopes. Now, a polarization microscope has a polarizer, and a condenser, an objective, and a birefringent material which is used as a compensator, and then an analyzer. And the polarizer produces plane polarized light with its electric field vibrating in one direction, and that's a non-east-west. And the analyzer is made out of the same kind of polarizing material as its vibration direction lined up in a perpendicular direction. We call it north-south, but it's in and out of the board here. And it extinguishes the light that comes from the polarizer. So the light that can enter the analyzer is generated by the modification of the plane polarized light by the specimen or by the compensator. And this works simply in the following way, that if the plane polarized light hits the specimen, the bioprinted specimen generates two orthogonally polarized light waves. They move through the specimen at different velocities, depending on n sub e and n sub o. And when they exit the specimen, because of these different velocities, there's a phase difference between the two light waves. And this phase difference is called retardation. And retardation can be measured in nanometers. It's n sub e minus n sub o times the thickness d, and or in radians, which is 2 pi times retardation divided by the length of light. Now, this retardation can't be seen by eye. The light intensity still looks the same to your eye, but if you put an analyzer on the light path, then what comes through the light path has this equation form, sine squared of the retardation divided by 2, and if we plot this out as a function of specimen retardation, we start with 0 here with no birefringence or no thickness, and we get maximum brightness coming through at a particular wavelength for a half wavelength retardation between the E and the O layers. So this is a quantitative technique that measures the product of birefringence times thickness, which is retardation, and for something like the spindle, the actual measurement of retardation tells us about the number density in a cross-section of the spindle and how many microtubules we have there, for example. And if you look at our spindle here, in the presence of a compensator, another birefringent object that has its n sub e axis this way, n sub o axis that way, the larger refractive index in this case being the n sub e axis, and the larger specimen with that compensator, and these two retardations add together to make a larger retardation, which makes a brighter light, and it brightens the central spindle, and it brightens the aster. But for the astral fibers going this way, their axes are in opposite directions, and so we get a negative compensation, which actually results in a lower total retardation. And since the background is produced by the compensator retardation, this is lower than that produced by the compensator retardation, so it appears darker than the background, whereas this part appears much brighter than the background. And that's how compensators help both brighten the image in the specimen, but also can give you dark contrast, but obviously we're going with fibers in this case. So one of the important examples for the use of polarization microscopy was performed by Shin Henry in the early 1950s, where he developed a polarization microscope of sufficient sensitivity to image living cells in mitosis. And the results of this were very important in the field of cell biology, because it was the first proof that spindle fibers were not a fixation artifact. And so this movement of the really polymeric cell, and the brightness here, the brightness of the spindle fibers shorten and pull the chromosomes up to the poles until you make the nucleus, and then another brighter wave forms here at the position where the cell plate is formed, and we now know this is a mid-zone microtubule complex that's used to support microtubule motor trafficking that brings vesicles that builds the cell wall and the nucleus membrane. Now, here we are 60 years later, and now in polarization microscopy, electronic compensators can be produced by using liquid crystals and controlled by computers, and Rudolf Oldenburg and his colleagues at the Marine Biological Labs have built a microscope called the LC Polescope, in which images can be obtained, in which the magnitude of the intensity is, for each pixel in the image, carries information about the retardation independent of the orientation. And this is a movie of that, so there's no orientation dependence anymore, and so the brightness of this image is directly proportional to the microtubule number and the thickness of the fibers at this stage. This is true for the plasma membrane cortex or for the mitochondria that are in here. And these are mitochondrial bundles that are coming in here at the end. And so a great deal of quantitative information can be gotten from these sorts of images now, as well as just being able to see structure and transparent cells by this type of technique. Now, the last type of transmitted image contrast mode that I like to talk about is differential interference contrasting. People are very frustrated with phase contrast, particularly when trying to image thicker specimens, because the organelles, like this nucleus here, some of these mitochondria, although nice contrast was produced in phase, around the edges there was a white halo that's typical of phase contrast images. You can see it here for the nucleus, you can see it down here for the edge of the cell, and in thicker specimens these halos acted like the edges of Garfield, and they accumulated through the depth of the specimen and made optical sectioning very poor. And so the invention of differential interference contrast by Namarsky and Smith in the 60s, and its implementation by initially by Zeiss and Leica was quickly accepted in the cell biology field, because this technique highlighted edges and was less sensitive to the absolute mass of objects. And so here we can see the typical image for the same cell. This is a DIC image, and this is the phase image. And I know here that the edges are very sharply defined, and in fact, the thickness of the specimen gives the same contrast as the background, and therefore doesn't carry through as you do optical sectioning through the material. So how do we get this? Well, DIC is actually a polarization microscope, and it has two additional biofringent components, a condenser DIC prism and an objective DIC prism, which together make a dual beam interferometer that functions as defined here. So the lower DIC prism splits the incoming polarized light beam into two equal amplitude orthogonally polarized light beams that can't interfere with each other, and these pass up through the condenser and then through the specimen. And one beam coming through the middle of the lower prism is shown here, and as they pass through the specimen, these two light beams are sheared apart, that is, they're separated by a very small distance, which is called the shear distance, and this is set by the manufacturer to be about half the limited resolution of the microscope and condenser optics. And so, at the specimen, these two wavefronts, the E and the O wavefronts are lined up with each other. When we move through our transparent specimen, we now have this retardation that takes place for both wavefronts. Then we pass through the condenser, and we also pass through a biofringent compensator. And the compensator advances one wavefront over the other, and the objective prism realigns the two beams so their edges come back together. And that process of realignment causes a shift in these two edges, so that when these two wavefronts pass through the analyzer, they're no longer lined up with each other, no longer in phase, and we have a phase difference. And because of this offset induced by the compensator, on one side the phase difference goes negative, and on the other side it goes positive relative to the phase difference in the background. So this produces the one edge being darker and one edge being brighter than the background that we normally use for compensation. We switch the compensator the other way and advance the other beam to the other one and shift the direction which you see for the edges. So that's how DIC is produced conceptually, and we usually adjust this compensation to be about a tenth of the wavelength, and that makes the highest contrast for the edges. And I'm going to show you some pictures of embryos, and in particular these are early embryos of the monogenetic organism C. elegans, it's a worm, and the picture we will begin with, the sperm is here on the right-hand side, maybe a short time previously, and the sperm nucleus is decondensed and formed the sperm pronucleus here when the movie starts. And so we're going to look at the first four cell divisions, and over here, on the other side of the cell, this is the female pronucleus that's formed after going through its... And so we're going to see pronuclear movement, that is the movement of the two nuclei that comes together, and that's because the centrosome that the sperm brings in makes a microtubule aster here that actually reaches out and grabs this other nucleus and then pulls them both together, as well as moving them into the center of the cell. There's first division, and then now we have interphase, and now we have second mitosis and division, and into third. So you get very nice clear optical sectioning with this DIC, which would not be possible with phase contrast. Now here's another important feature of using transmitted by microscopy, which is this worm has a small number of total cells that make up the organism when it's a finally mature organism, and investigators have been able to use DIC microscopy to actually follow the development of all of these cells and their relationships to each other during morphogenesis, cell divisions, and morphogenesis in this process. And I'll show you the first example from Bob Goldstein's lab. This is just the beginning of first mitosis, and first division, second, third, fourth, fifth, So this is all for one focal plane, and what you mainly see are the nuclei or the big round objects here. Right? And the beauty of this is we're able to image this organism using a green filter and a very good heat reflection filter almost all the way through to the final formation of the adult worm and before hatching. And they've even developed techniques in DIC so that it can take 4 different focal planes at the same time and then time-lapse all 4 of them. Right? And so use this information actually to build this developmental map of where all the cells are relative to each other in the developing organism throughout these many stages of development and making the final mature organism. This would be impossible to do in fluorescence microscopy because absorption of light inevitably hurts the specimen, whereas here we do not have absorption of light. So I hope you enjoyed these examples of these 4 modes of transmitted light imaging, and I hope you have a chance to get in the lab and give them a try.
Hi, I'm Nico Stuurman. I'm a staff scientist at UCSF, and I prepared this lecture together with Kurt Thorn, who's director of the Nikon Imaging Center at UCSF. And I want to start out with presenting to you this nice, complicated new microscope system that we have in the lab. So here we have a microscope system that we use in the lab every day. Actually, people fight for time on this system. You recognize here probably the microscope body itself with the eyepieces. There's the objective lens down there. There is a motorized XY stage sitting here that I can control with the joystick or from the computer. Then here on the sides we have a spinning disc confocal unit, and elsewhere in the course it will be explained how that spinning disc works. But then here we have a very fundamental part of this microscope system, and that is a digital camera. So this digital camera is the thing that actually registers the image, it collects the image, and then sends that image through a cable to something else you will recognize, that is a computer. The computer can then hold the digital image in its memory, or can write it to disk, or can display it on the computer screen. And here in the computer we can do all kinds of manipulations, so we can visualize the data, which is something you always want to do, but we can also do analysis, digital image analysis on these images, and extract quantitative information about the things that we see in the microscope. And so in this lecture I'll first be explaining to you the principles of how a digital camera works, and then also give you a very basic introduction to digital images and digital images analysis. So we're going to talk about cameras, and to just give you another idea, this is another camera. It's a box, it has a bunch of electronics in it, often it has something like cooling, but the part that is really important is shown here and blown up here in this figure. It's the chip with photosensitive elements. So it contains rows and columns of photosensitive elements that we often call pixels, pixel elements, and so each of these pixel elements is able to detect a flow of photons. Now, to give you a bit of a schematic overview, one blown up here, photons are coming in, and by this semiconductor material through the photoelectric effect are converted into electrons. Those electrons are stored for the duration of the exposure in a potential well, and then at a certain point in time the number of electrons is being read out and transferred as a digital number to the computer. A bunch of parameters with these pixels that are of interest to us. So for instance, the most basic one is like how large is a pixel, its width and height. And we have an example here of the Sony ICX285 chip, which is a CCD chip that has been used now for years in microscopy, very popular chip design, and that has pixels of about 6.5 microns square. The other number that's important is how many we have, so how many rows, how many columns. If you actually multiply it by this number, you get the physical size of the chip. And so for the ICX285 chip, that has about 1,400 columns and about 1,000 or so rows, for a total of 1.4 megapixels. And you see this is much less than most of our cell phone or digital cameras or digital SLRs have. So how many pixels do we actually need in a microscope? And we know that if you have fewer and fewer pixels, you get a blockier and blockier, a more pixelated image. And so you know that that is not good. So too few of them is clearly not right. But if we have more pixels, is there a point that it doesn't make any sense anymore? And clearly there is such a point. And when you think about that, is what you try to do is to match the pixel size that you have to the resolution of your microscope system. And so how do you match the two? Well, people in the signal processing world have thought about this problem for many, many years. And so a long time ago, they've come up with the so-called Nyquist-Shannon sampling theorem, and that states that for the smallest limit the smallest distance that you can resolve, you will need at least two digital samples. And so in practice, in a microscope system, that means that we need 2 to 3 pixels to cover the resolution limit of the microscope. And so what is the resolution limit of the microscope? And so you've seen in other lectures that there are various criteria for determining that. And as an example here, I'm using the Rayleigh criteria. If we now have a 100x lens that magnifies 100-fold with a numerical aperture of 1.4 NA, and we assume green light wavelength of 500 nanometers, then the Rayleigh criterion states that the resolution limit, the shortest distance within which we can still discriminate two point objects, is given by 0.61 times the wavelength of the light divided by the numerical aperture, and that in this case leads to a number of about 220 nanometers. Now, since we have a 100x lens, that means, so we need to multiply that 220 nanometers by 100 in a camera plane that then corresponds to 22 microns. Now, according to the Nyquist theorem, we need at least 2 pixels for every 22 microns, and that means that the pixels need to be 11 microns or smaller. And so, for instance, our ICX285 based camera has 6.5 micron pixels, so they clearly would fulfill here the Nyquist sampling rate. But whenever you buy a camera and want to match that to your existing microscope, these are the kind of calculations you would want to make. Now, in microscopy, especially in fluorescence microscopy, we barely ever use color cameras. And why is that? Well, that follows from the design of color cameras. So color cameras actually have the same kind of chip, a monochrome chip. However, in front of each pixel element, a small colored mask has been put. So, for instance, in this Bayer mask, and that is what most RGB cameras use, every 4 pixels will have 2 that have a green filter, 1 blue one, and 1 red one. And that now means that when you have a green photon hitting this Bayer mask, that only the ones hitting half of these pixels will actually make it and be detected, and the ones that hit the other half will not be detected and you lose them. So a lot of light is being lost. And in fluorescence microscopy, we really like to put filters inside the microscope, and we can design much better filters than the ones over here. Of course, in things like observation of histology sections, where you care much less about light loss, color cameras are totally fine, but for fluorescence microscopy, you want to use a monochrome camera. Another parameter in cameras that is very important is their sensitivity, and the most important parameter there is the quantum efficiency, and that means of the photons that actually hit the cameras, what fraction is converted into an electron that I can then later read out and actually see in my computer. The quantum efficiency depends on the chip design. So, for instance, these back-thinned CCDs can have a very high quantum efficiency, up to 95%. Quantum efficiency is also wavelength dependent, so you want to make sure that it matches the dyes or the things that you're looking at. Nevertheless, many cameras nowadays will have between 70 and 95% quantum efficiency. So there are other sources of noise in cameras. However, when we start talking about noise, the very first thing to realize is that there is noise present in any light signal. And that is due to the fact that your camera measures photons. And photons are particles. So particles will, even though the average of the stream is constant, they will not arrive at the pixel element in a very regular way. They